Hi, my name's Andrew McLaren. Today we're going to talk about electron filling orders and how sometimes you have an exception to this. Now, what I've got is marked in purple, this diagram that usually people do. It's kind of like this way of tracking what you need to fill in and when. This, according to this, says that you should be filling in 4s before you fill in 3d. And that generally is appropriate if we're talking about something like hydrogen, because these orbitals they stagger in higher energies for the different shapes. So like P is higher than S, and like D is higher than P. But something weird happens around like this 4s and 3d, where even with hydrogen, they're pretty close to each other. So 4s is just barely getting filled before 3d. And there's some factors that can actually make 3d and actually a lower energy level. So in what I've drawn in here, this is half filled. There's stability from that. So as I've written in green here, there's stability when we have a half filled shell. That stability can actually cause this to be a slightly lower energy level than the 4s. In addition, if we completely fill this in, that gives you additional stability. So if you can get this completely filled in, then that is very stable as well. So it'll be a lower energy level when we can completely fill in our 3D. So you can see right here, copper is going to be thought of as the 4s being a higher energy level than the 3D. So when we're talking about copper here, it looks something kind of like this. And if you were to take one electron away from copper, then you're going to be taking it from that 4s level. This is a bit improper. Normally you still write this with like the 4s in front of the 3D, but you can think of it as a higher energy level. And a lot of your exceptions to your electron fill orders are going to be things where, like, if you could just bump one electron up from the S up to the D, then you get either a half filled shell or a completely filled shell. So you can see, like, what I've got in orange right here, this and that, they have half filled orbitals. So we're kind of bumping up something from that 4s or that 5s into that D shell, and because of that, it gets to being more stable. And overall, if we can have more stability, then that is preferable. So electrons will come closer to the nucleus if they can. It's kind of like a ball rolling down a hill. If it's possible, it will happen. So these diagrams generally are thought of as what we think of with like hydrogen or something pretty simple, but it gets a bit more complicated when you start filling in other energy levels. Here's another more complete list of exceptions. Not all of them have half-filled energy levels, but that's a good explanation for things like our chromium right there or our copper here. We can see that those are having full or half fill orbitals, so that helps us explain why it's written that way. Now, to help you see from a good source, this is the AP chemistry exam. They're a very reputable source, not just something online. You can see for the question one right here, they're talking about manganese or Mn. For manganese, you still write the 4s before the 3d, so that's how you would really should be writing it. But the 4s really should be thought of as the higher energy level. So if you're taking manganese right here and you're turning it into an ion, manganese forms a +2 ion. You can think about that as you taking away like 2 electrons from your 4s. So it's empty. It's an empty shell. And you wouldn't want to take 2 electrons from the 3D because that's not a full or half-filled shell, so that doesn't help us get to a stable configuration at all. So there's a lot of different ways to think about this, but it really comes down to stability. Um, and that's the best way of thinking about these exceptions. I did ask ChatGPT to help me come up with a mnemonic to help people remember what are some of these exceptions. So we've got crazy monkey catches shiny apples. You can kind of see how that works. And then also crazy moose can sing always. So just like some little mnemonics that can help you remember what those exceptions are. But it's more important to think of them as like lining up in a similar part of the periodic table, like chromium and MO. In both those cases, they're getting a half-filled shell by bringing an electron up from that 4s. And that bringing it up actually lowers that 3D orbital to being a lower energy than the 4s. That's how you want to think about this. Now, I did ask ChatGPT to explain this a little bit, so it does have a decent explanation here, um, and I'll share that in the description as well. But this diagram it looks kind of backwards because the higher energies are lower than on the diagram, so that's a little bit confusing. And I liked its explanation for the exceptions. So the exceptions where we don't have a half filled or a fully filled, there's essentially you're spreading out the electrons a little bit better in doing these weird configurations. So there's a balance between s and d orbitals. You can also think as s as like a sphere. So if you can put electrons just in that sphere, they kind of balance themselves out anyways. D orbitals, they're kind of not dumbbell shaped, but they look kind of like crosses, and they cancel each other out when you have an electron present in all of those different parts. So the electrons are nice and evenly spread out when you do that. But it's kind of nicer to think of an s orbital as just being a nice sphere and putting electrons there if possible. So it's a combination of those two things, and you want electrons to be away from each other, but also still close to the nucleus. So yeah, if you have any other questions about electron exceptions for the fill orders, please put those in the comment. I thought this is a concept that can be very confusing, but it really boils down to one major word, which is stability, and the fact that this actually becomes higher and lower depending on if you've got a full or a half full shell, which just moving it up and down like that, I think helps people see pretty clearly.